Okay, it is 2:05, so time to start. Welcome everyone. Thanks for joining us for the first of this series of two Cirrus webinars on NVIDIA GPUs, taking place today and on Tuesday next week, same time and same venue. It is my pleasure to introduce Paul Graga, formerly from the EPCC Paris, now Senior Solutions Architect at NVIDIA. The title of the presentation is Making Efficient Use of GPUs for High-Performance Computing. The floor is yours, Paul.
Thank you very much, Juan, and nice to see you again. So as Juan said, I'm going to be presenting a couple of talks. Today's is more focused on the programming side and specifically the HPC programming side. And next week's is looking more at the deep learning and AI and data science side of things. Next week's is, I would say, a bit more aspirational. It's looking at the sort of art of the possible is what we would call it, give you some ideas of what is possible to achieve using AI and GPUs. This week, I think, is very much more, if you are developing your own applications, here are some tips on how to make sure they work efficiently. So let me just, I'm going to switch off my camera and share the screen. Hopefully you can hear me okay. If you have any questions during this talk, I'd be more than happy to answer them. I'm not sure I'll be able to see the chat, so if I don't respond straight away, feel free to open your mic, or one of the admins can pass on the question. Okay, hopefully you can hear me loud and clear. If I do go over anything too quickly, I'm more than happy to cover it again. I do tend to talk quite quickly. It's because I grew up in Newcastle and we speak very quickly down there. This is me already at about half speed compared to what I normally talk like. So please let me know if I'm going too fast for you. As Juan mentioned, I'm a senior solutions architect with NVIDIA. Previously, I worked at EPCC for about 20 years. I worked in the porting codes onto supercomputing systems. I'm working both in industry and academia. Then I went to NVIDIA, where as a solutions architect, I give training and advice and recommendations on what GPU is suitable for which job and how to get the best use out of those GPUs once you have them. So today we're going to be looking at the HPC side of things. So let's move on. Now, I asked a question in the chat there just to try and get a bit of understanding of the experience of the people watching today. And that was really useful. So thank you for that. I would say you averaged out at about 2 on a scale of 1 to 5. So that's good. So the first few slides, I'm just going to sort of cover a bit of the background of GPU computing, how GPUs are different from CPUs, and the sort of generic approach to programming for them. For some of you, this may be stuff you already know and be very basic, but what it will do is ensure that everyone attending is starting from a similar point of knowledge, okay? So that's why we do this. So many of you might be aware of NVIDIA's relationship with HPC and AI, and more generally with the rise of GPU computing. But if you aren't, here's a visualization which I think is very helpful. So one way to look at it is that over the last 40 years or so, people have relied heavily on the trends on the graph here on the left, as dictated by Moore's law. Essentially, the CPU and single-threaded performance basically got predictably faster year over year. So you could just buy a new CPU or a new architecture every couple of years, and your application performance would increase. Unfortunately, what we've seen is the trend has plateaued. You can only really squeeze so much performance out of single-threaded instruction sets. You can only make your transistors so small. And what's happened in the last 15 or 20 years or so is that we're seeing the rise of parallel computing, and more specifically GPU computing, as a paradigm that allows us to get back on this trend of increasing performance year over year as it relates to user applications. And the way that's possible is by a combination of using a general processor, like a CPU, in combination with a massively parallel architecture like a GPU. So you take the sections of the code that are really computationally intense and parallelizable. It's typically a small fraction of the overall code, but by far the most time consuming. And you run those parts on the GPU, which allows you to, in many cases, achieve orders of magnitude of speed up. So let's look a bit more at the differences between the CPU and the GPU architectures. As we saw from the graph, the increases in individual thread performance of CPUs has been stalling. So in order to try and counter this, CPUs have moved to an increasingly multi-core architecture. You see many of the modern CPUs have 128 cores on them, and they have very fast clock speeds as well. CPUs also have a large main memory. We see servers now with terabytes of RAM, but we should know that the bandwidth of that memory, which is how quickly we can move data about, is actually relatively low. CPUs are designed to run multiple, multiple different applications at once, such as running an operating system with all the associated services, or running your word processor alongside a browser. So individually, these tasks and applications are essentially serial in nature. So each of these applications is assigned to a single thread or a small number of threads, and these are scheduled in a time-sliced manner to run on the CPU. Then a given thread must get as much as possible accomplished during its time slice. And one of the consequences of this is that you require low latency. What do we mean by that? Well, we want to minimize the delay between issuing a request for data and actually executing the instructions on the data. And on the CPU, that implies having large caches to hold the data required by all these threads, complex control logic to ensure, for example, that the data is ready to go when the thread is running. One of the consequences of this is that a large amount of the silicon on a CPU is actually dedicated to this movement and prefetching of data, which has an impact on the performance per watt of the CPU, because a lot of the energy is spent moving data around rather than actually performing calculations on it. And also, if you have things like cache misses, which is where you're trying to access data which isn't already in the cache, that can be very costly as well in the CPU and cause things to stall. Then we look at the GPU, which is quite a different beast. So GPU is, the history of the GPU, of course, is that it was designed for generating images on a screen. And to do that, it would perform the same operation many times across many thousands, if not millions of pixels. And of course, that's a very, very parallel operation. So the GPUs have been designed from the bottom up to perform parallel tasks. Modern GPUs have a huge number of compute cores, over 10,000 for some of the latest cards. But these compute cores are much more lightweight compared to the CPU ones. They don't have the complex logic for prefetching of data, for example. So how do GPUs deal with latency then in this case? Well, they deal with it by hiding the latency with more computation. Essentially, we give the GPU much more work to do than there are physical cores to execute it, which is a very different approach to the CPU. So the way that works is we have the schedule on the GPU, which launches a thread or a team of threads. That thread tries to execute an operation, such as an addition. If the data is not there ready for the thread to use, it issues a fetch command to memory, and it stalls while waiting for the data to arrive. While that thread's stalled, the schedule then moves on to another thread to execute its instructions, and so on and so on. And what this does is create a pipeline of issued instructions across a series of threads. So whilst we're waiting for the first thread to get its data, other threads can be executed. And this switching between the threads hides the latency of the memory fetching and the issuing of instructions. And thus, the more work we can give the GPU to do, actually, the easier it is for the scheduler to hide this latency. So this is quite a key point about the GPU. We need many overlapping concurrent threads. And this is a core difference to how we program for the CPU, where we usually just match one or two threads to a single compute core. To help support this, GPUs have a very large register file, and that holds the state of the threads. And switching between the different threads happens at effectively no time penalty at all. It's even as often as every clock cycle. One of the consequences of this is that the significant majority of the silicon on a GPU can be given over to computation rather than the data movement, which gives them their very efficient performance per watt. Now, we mentioned memory as well. So the GPUs have a very high bandwidth main memory compared to a CPU. And given that many applications are bandwidth bound rather than compute bound, this high bandwidth memory can also deliver significant performance improvements. However, this additional bandwidth does come at a cost, with the GPU memory usually being significantly faster but relatively smaller than the CPU memory. So, for example, the very latest A100 card has 80 gigabytes of GPU RAM on it, which is large for a GPU, very large for a GPU, but relatively small compared to the CPU. However, that 80 gigabytes runs at a massive 2 terabytes a second of bandwidth, which is pretty much an order of magnitude faster than CPU memory. Something else we have to consider with GPUs, which is quite different from CPUs, is the precision that we want to use for our simulations. So the compute cores on a GPU are often dedicated to calculations at a particular precision, such as integers or single precision or double precision. So different GPUs actually have more or less of these. For example, the V100, which we'll be talking about today, are ideal for double precision calculations, as they have a large amount of the double precision cores, whereas perhaps the RTX cards, for example, are aimed more at single precision performance. So again, it's just something to bear in mind when you're making a choice about which GPU to use. So let's go through a bit of terminology. So GPU computing is a type of heterogeneous computing. That is parallel computing with multiprocessor architectures. In GPU computing, many core GPUs are combined with multi-core CPUs in order to achieve high performance. So the CPU and GPU have distinct memories. Actually, just to recap, CPU's memory is generally larger but slower. GPU memory is generally smaller and faster. But we need to communicate between the CPU, the host, and the device, the GPU. And we need to move data around between those two things. And that usually happens via the PCIe bus on the board. And you must know that PCIe bandwidth is usually much lower than either the CPU or the GPU memory's bandwidth itself. So one of the top tips for programming for GPUs is trying to avoid these data transfers between the host and device as much as possible. Or if you can, hide the transfer by performing computations at the same time. So let's look at the basic processing flow. So we start off with our code running on the CPU. We have some data we want to work on in parallel. That's currently on the CPU memory, so we need to copy that over to the GPU memory. Once it's on the GPU, we load up the program we want to execute on that code. So it's called a GPU kernel. Whilst that kernel is running, it may make use of the different layers of memory within the GPU. I won't dive into the details of that today, but again, it's something I'm more than happy to follow up on after the event. If people want more information, I can point them to the right place. So we load up our GPU program and execute on the data on the GPU. And then usually, once the GPU is finished doing its work, we may want to finish off on the CPU, perhaps do some I/O or something like that, or so do some checking. So we move the data back to the CPU. So that's a very simple data flow. And the idea behind all this is we can make small changes to our code. Usually in many codes, there's a couple of for loops or do loops in the center of the code, which are the most computationally intense functions. And they take up, whilst being a small number of lines in the code, they take up, a significant proportion of the execution time. And if those can be parallelizable, those are the ones we want to offload onto the GPU. Meanwhile, the rest of the code remains on the CPU. And by making these small changes, hopefully we can see a big speed up within our codes. Okay, I'll just pause there. Give people a chance to ask questions. Okay, no questions so far. If there are questions in the chat, I definitely can't see the chat, so please feel free to unmic and ask away. So let's look at the hardware which we have in Cirrus. So it's the V100 SXM2. I'll explain what that means in a moment. So the V100 is a fantastic card. It has 7.8 teraflops of double precision floating point performance. So remember, I said that these cards are excellent for double precision performance. It also has double that performance of single precision performance. So if your application can manage with just single precision, for example, many molecular dynamics codes can manage just with single precision, then you can take advantage of that. It has this thing called tensor teraflops, and I'll speak about that in a moment, but essentially there are some specialized hardware units on the V100 dedicated to doing matrix multiply and accumulate operations. And as I said, these are specific bits of the GPU, dedicated hardware just for doing that operation. And that's where that performance figure comes from. But we'll look at a bit more in detail on that in a moment. It has 16 gigabytes of the very fast memory, 900 gigabytes per second peak bandwidth for the memory on this particular GPU, and has a 6 megabyte L2 cache on it as well. Now, EPCC kindly shared this diagram of the layout of the nodes on Cirrus. So there are 4 of these V100s on each of the nodes. So you can see on the right there, GPU 0 through to GPU 3. Now, what I'd like you to take note of here is that there's little arrows between each of the GPUs, and that's because they're connected by NVLink. And what this NVLink is, it's a very high-speed connection directly between each of the GPUs, which allows you to do inter-GPU communication without having to go via the PCIe bus or via the CPU. So that can speed things up significantly if you're doing multi-GPU codes. Okay, so many of our libraries and many of the applications actually take advantage of the fact that NVLink is there without you having to do anything different. It just, the runtime drivers detect the hardware underneath, and if they see NVLink, they will use that for doing the communications between the GPUs. So you can take advantage of that technology very, very straightforwardly. Um, okay. So we mentioned tensor cores. So these were first introduced in the V100 and the VOLTA generation of cards. And as I mentioned, these are hardware units on the GPU which are dedicated to performing matrix multiply and accumulate, or MMA, operations. And they can perform many of these per clock cycle. Now, these were originally aimed at deep learning applications in order to provide hardware support for mixed precision calculations. For example, on the V100, we can take in single precision data. We actually perform the multiplication at half precision, that's FP16, but then we accumulate back into single precision. And this gives us a huge speed up over just doing standard matrix multiply on standard CUDA cores. And you'll find that for those of you who don't work in deep learning, this is a really useful way of performing calculations. Many of the calculations at the heart of deep learning are matrix multiply and accumulate operations, and you can manage to get the same results out of the networks that you train by using this mixed precision approach without any real impact on the accuracy of the models that you train. So it's a fantastic way to do that. But of course, there are also applications in HPC which can make use of these tensor cores at mixed precision. Also, as we come to more recent generations of GPU, we have the Turing and the Ampere cards. On the Ampere cards, we actually now have full FP64 support on those cards. So again, that's great for various HPC applications, as well, of course, still being useful for deep learning. Okay, now I'll have a look at a few of the different ways we'd recommend for programming for GPUs. And of course, there are various ways to do this, and depending on where you are in your GPU journey, the most likely way that you'll first experience using a GPU in your system is via an application which has already been accelerated for the GPU. And we'll have a look at a few of those in a moment. Also, there's various frameworks which are accelerated for GPUs, such as deep learning frameworks, TensorFlow, PyTorch always comes to mind. And they can automatically take advantage of the GPUs that they're running on. And in addition, what I'll talk about in next week's talk as well, we have many deep learning frameworks aimed at particular fields, such as healthcare or robotics, or physics simulation and AI, and I'll look at those frameworks next week as well. But again, the idea behind all these applications and frameworks is that you actually don't need to be concerned about the fact you're running on the GPU. The application will take care of that yourself. The next step that people maybe would look at is looking at using libraries. So of course, as HPC programmers, we all understand that there are various libraries for doing certain things. We have the BLAST libraries for linear algebra. And of course, the good news is that there are many GPU versions of those libraries. So you can just drop them in the same way that you would a standard BLAST library and take advantage of the GPU that way. Then we'd move on to perhaps a directives-based way of programming. This is where you add directives to your code. So directives are basically comments within your code which point out to the compiler parts of the code which you either want to be accelerated on the GPU, or parts of code where you want the data to be moved. And so I'm thinking of things like OpenMP and OpenACC would be the most commonly used way of doing that. And that gives you great portability as well, because of course your code doesn't have to change much. It just has these additional comments in it, which of course may allow the code to run on a multi-core CPU or on a many-core GPU. And then, of course, to get the maximum flexibility in terms of what you want to do, maybe there isn't a library which supports exactly what you want to do, or you want to make sure you get absolutely the maximum performance out of your GPU. Then you go down to the sort of device-specific programming languages, and that usually requires the most effort in terms of getting up and running, but can be the most rewarding in terms of the absolute performance. Quite often, though, you see that people mix and match several of these. Okay, you may use libraries in part of your code, use directives in other parts of your code, along with the device-specific languages for the very, very key parts of your code that you want to accelerate the most. So you can actually mix and match these in various ways, depending on how large your code is and which parts of the code you're most interested in working on. So I mentioned the apps and frameworks, so I'll just go through a few of them here. So all the major deep learning frameworks, PyTorch, TensorFlow, etc., have GPU accelerated versions available. The top 15 most used HPC apps globally all have GPU accelerated versions. And of course, there's thousands of apps in a huge range of fields. And I've put a link there to a catalog where you can get an idea of that huge range. Of course, we have domain-specific frameworks. I'll speak about those a bit next week. I mentioned here is just a list of some of the HPC apps. Many of these which are actually mentioned on the Cirrus website. So there's many of the people on Cirrus making use of these. All of these perform very, very well on GPUs. I've put a link there which gives you an idea of the performance you can get for a series of benchmarks on the GPU versions of these as compared to the CPU. And I've just put a few figures at the bottom there just to explain what this means. It looks a bit hard to understand, but so NRF is called the node replacement factor. So basically, this is how many GPU nodes, how many CPU nodes would be required to perform the same amount of science as a single GPU node. So the single GPU node here I've represented as 4 times V100, which is a Cirrus node. And so if you're running GROMACS, on the link I provide there, you can see you need between 10 and 14 CPU nodes to get the same throughput as a single GPU node. For LAMPS, between 9 and 44, depending on the benchmark. And for SPECthem 3D, you would need 53 CPU nodes. So this just gives you a broad idea of the kind of range of speedups you can expect by taking advantage of GPUs. And this is why people use GPUs. Of course, not every application can exploit the GPUs, or some aren't quite as mature, but certainly in the major HPC apps and the list I presented here, you know, the community puts a lot of work into making sure these applications can run as quickly as possible on GPUs. And of course, we put a lot of work into that as well. It may actually surprise you, but we have more software developers at NVIDIA than we do hardware engineers. And that's purely because the software side of things is so important in terms of getting the best performance out of the devices. So we mentioned libraries as well. Obviously, we have a wealth of libraries. I think there's over 100 now. Just touch on some of the major ones here. So cuDNN, that's the Deep Neural Network library. That's the library which underlies a lot of the deep learning frameworks. We have all the linear algebra libraries, QBLAS, QSparse for doing sparse matrix operations. We of course have the CUDA maths library, QSolve for doing you know, C++ type solutions. We have a relatively new one called cuTENSOR, which is basically looking at matrix operations, but taking the matrices to higher dimensions. So basically multi-dimensional matrices, which is what tensors are. And again, that can be as many applications in the world of HPC as well as deep learning. We have, you know, FFT libraries as well, which can interoperate, have the APIs on those look very similar to the APIs you see on your typical FFT libraries you'd see. So all of these should be quite straightforward to drop in. And again, I just wanted to stress the key thing to take away from the fact that there are all these libraries available is that you should try and keep your CUDA installed up to date, because we are constantly working on these libraries. They're not a fixed point in time. We are always developing, and whenever a new piece of hardware comes out, again, we try to work very hard to make sure it works as well as possible with that piece of hardware. Also, many of these libraries can exploit the features on the GPUs without you needing to worry about it. So the libraries, QBLAS, for example, QSolver especially, can make use of the tensor cores for doing the matrix multiply and accumulate operations. And in fact, I think QSolver now supports doing mixed precision iterative solvers as well. So that's a really good way of taking advantage of the hardware, but all you have to do is make a library call. You don't need to worry about programming directly for the tensor cores. So we mentioned directives as well. So this is the next stage here, just a very simple example on the right. This is an OpenACC directive in C. And essentially we use hash pragma, which basically says to the compiler, this is a directive, ACK for OpenACC. And then kernels basically just says the next parts of code we want to try to run as kernels on the GPU. And of course, there are similar operations available in OpenMP as well, which I know is very popular approach from the CPU side of things, which can also be used now to exploit the GPUs as well. So what you get here is something which is very portable, but still very performant, and hopefully you won't have to make too many changes to your code other than adding these comments. And then we get into the more deep GPU programming languages. So there was lots of these around. Of course, the ones those of you who've used CUDA in the past will be familiar with CUDA C++ or CUDA Fortran. Of course, we have CUDA Python now as well. Python is becoming a language is very popular in the scientific community. And of course, we support programming for GPUs in Python as well. And there's a few different ways of doing that. Again, you can use NumPy, for example, or we're now trying to bring Python up to be a first-class citizen in the sense you can program for Python the same way you can program for Fortran and C++. Also, we have, I've highlighted in green here, ISO Fortran and ISO C++, and basically the standard languages actually have built into them ways of expressing parallelism. And the new generation of NVIDIA compilers can actually support that so that you can compile parallel code for a GPU using just the standard languages. That's no libraries, no directives, no device-specific instructions. It's just using the pure standard languages, and I think that's a very powerful approach we'll see being taken up more and more. And I'll go into a little bit more detail about that in a moment. And of course, there's other language extensions outside of this. So CUDA C++, CUDA is the extension to C++. The various other ones out there, things like Caucus, Raja, Sickle, all of which have varying levels of popularity and allow you to write your code in the most portable way. But at the fundamental, if you want to get the absolute best performance out of the device, you are going to need to go to a device-specific language. But of course, you can achieve very good performance without having to do that. Okay, so let's just look at where we are with the state of the art in GPU programming. I'm actually going to start on the right here, which is going in sort of chronological order. So before 2007, people we're starting to experiment in using GPUs for doing scientific applications rather than just for putting pixels on a screen. But the challenge was there, the way you program for the GPUs, you have to program for shaders and graphics APIs, and that didn't really match well to what the algorithms were actually trying to do in HPC. So it was quite awkward to do and quite niche, and very few people that were able to properly leverage the power of the GPUs back then. And in 2007, we introduced CUDA, Compute Unified Device Architecture, and this allowed you a way of expressing your equations or your HPC codes in a way that was familiar to the programmer, but they could be run on the GPU. And this was a great leap in terms of accessibility and improvement in developer productivity for programming on an accelerated system. And of course, we've had generations of CUDA have come along since then, making things easier, improving runtime performance. But of course, we recognize that developers need to write code that's portable across different systems and different tool chains. And so that's where the directives-based approach, such as OpenACC or OpenMP, come along. And that helps serve this purpose of making sure that the code's portable. Now, one of the new developments we've seen in the last year or so is trying to continue that path of making it as easy as possible to program for GPUs, making it easy to use and develop with, as well as the runtime performance. And that's using our toolchain to automatically accelerate features in ISO standard C++ and ISO Fortran. And so this means developers, you can stop thinking about porting to an accelerated system. They can just think about optimizing. And that's how you should look at this slide going from the other direction, from left to right. Developers today, I would recommend start by programming in what they're comfortable in, be it C++ or Fortran, and then let the tool chain actually accelerate that on the GPU. And then when you start needing to think about optimization, perhaps you want to start thinking about where the data movement happens. Perhaps the first step along that path would be to use the directives-based approach to try and incrementally optimize the performance of the application while still remaining portable. And then, of course, when you actually want to get down to the absolute best performance you're going to get out of the GPU, then you go down to the device-specific language, and of course, in this case, CUDA. So I think that's the way we're going to see people programming going forward over the next few years, I think. And just to give you an example, so on the left here, this is tiny writing, and you're not meant to be able to read it. It's there to represent this is what a code looks like with OpenMP directives in it. Okay. On the right is just a standard parallel C++ 17 code, and it's using you might be able to see the standard execution part, which basically says to the compiler, we'd like to try and run this particular STL function in parallel. Okay, you can see it's much neater, composable, compact, and elegant, as the slide says. Easier to read and maintain, and it's just the ISO standard. It doesn't rely on any third parties, doesn't rely on any directives. Okay, and of course it's entirely portable. as well. And you can use this to develop multi-core CPU parallel code as well as GPU code as well. That's supported as well. And let's see what sort of performance you can expect to get out of that. So this is looking at an A100, the next generation. So on the left-hand side there, you can see a dual Xeon Gold server, and then the C++ version on an A100, such that the same code, and we're seeing significant performance improvements on the A100 over the multi-core CPU version. And then just to see how well does the ISO C++ version perform compared to something which is more explicit in how it parallelizes, in which this case OpenACC, and we can see we get exactly the same performance. Okay, so it shows that we can deliver performance using this standards-based approach without having to go into using additional directives and so on. HPC programming in ISO-Fortran is also a possibility. So we have a compiler NVFORTRAN, and this can accelerate Fortran intrinsics such as mapmul, and it uses the cuTENSOR library in the backend, but of course that is transparent to the user. So on the left here, we have a sort of pretty standard matrix multiply operation, which of course can be expressed as the Fortran standard mapmul calculation function in the middle there, and on the right there we can see the different performance there. So the naive inline V100 version, which is the one on the left, just letting the compiler do its thing, we're not seeing fantastic performance there at all. So there must be scope for optimization. But instead of doing that, why don't we let the compiler take care of that using the Fortran intrinsics? That's what the middle figure there is. And if you recall earlier, the max performance, double precision performance we would expect from a V100, it was 7.8 teraflops. So we're almost seeing the maximum performance possible on a V100 there for this particular calculation. And it's just by using the ISO Fortran intrinsics there. And of course, on the A100, again, we're seeing close to the maximum possible performance. As well as supporting the intrinsics such as mapmul, we support the Fortran intrinsic of do concurrent, which can be used to replace one or multiple do loops. And again, we said earlier, the do loops tend to be where most of the time is spent in your code. So you can take advantage of that to automatically parallelize your code to run on either CPU or GPU. Okay. So we've looked at some of the apps and frameworks. We've given you some tips on how to accelerate, write your own code for the GPU. Now we'll touch on a few topics and features perhaps you haven't come across, which make sure you try and get the best out of the GPUs. They can be considered to be quite complicated pieces of hardware, so it can be a challenge to make sure you get the best use of them. And which is why we'd always say, first of all, go to the applications which are already accelerated. Go and use the libraries. A lot of work has been put into those to make those work as fast as possible. It's not always the case that it's going to be a library application which does exactly what you want to do. So let's just look at a few of the other ways of making sure we get the best out of GPUs. First of all, I'd like to touch on containers briefly. So quite a lot of the GPU systems we see being installed now are dual purpose. We get a lot of users from the HPC background, from the simulation background, and we also see a lot of users come from the deep learning background because, of course, the GPUs are fantastic at doing the calculations at the heart of deep learning. But what the people from the deep learning or the data science background tend to bring is the use of containers. So I'm thinking of Docker, Singularity containers here, because that's the sort of environment they're familiar with. And then they come into this world of Slurm and module load and things like that in HPC, and it can all be a bit confusing them. But I'm just going to try and motivate the case for why containers are a good thing. So on the left here, we have a very typical configuration of an HPC system. We have multiple versions of libraries. They all need to be maintained, and there's a complex web of interdependencies. But on the right, we have a much cleaner configuration when we use containers. Each app is sort of self-contained. This is why we use the word container, self-contained. Each app has all its required libraries in a self-contained configuration, separate from the other apps. And so I just want to go through a few of the benefits of doing that. So why containers? Well, it answers the question how to get software to run reliably when moved from one computing environment to another. So we can have, run anywhere OS kernel supports it. It gives us mobility of compute. It greatly reduces the time consuming and, of course, error-prone bare metal application installations. Anyone who's tried to install any vaguely complex bit of software will know that it's not a pleasurable experience. especially when you're moving from system to system. One of the key things I think for scientists who are performing simulations, it greatly improves your reproducibility. You know, rather than saying like, here's a version of the code I used and here's a data set I used and this is the system I run it on, you can just release the container, which can have all those things kept within it, and it captures that point in time when you generated the results for the particular paper that you're submitting to, and that can be easily shared for people to try and reproduce your results, and makes it much easier for them rather than someone else who wants to recreate your results, you know, trying to get access to a similar machine, trying to get access to similar operating system, similar version of the code, and then having to upload the data. So I think that's one of the key things for HPC. Of course, it gives you a consistent environment across the different platforms you'll be using, gives you more flexibility. And from an admin side of things, I think it really simplifies the deployment of software, and in particular GPU accelerated software, which can sometimes add an extra layer of complexity. And I think one of the key things as well, notice the performance you get using containers is very, very close to bare metal. You're talking 99% of bare metal performance. So there's really no, you know, significant performance impact, but you do get all the benefits listed here. And with that in mind, we have a great resource which has many containerized applications and solutions. So this is the NGC. It's originally short for the NVIDIA GPU cloud, but it's not a cloud of GPUs. It's actually a software repository. So I just call it not a GPU cloud now. And what we have there is, you know, containers ready to run of all the major deep learning frameworks, many of the HPC codes. In addition to that, if you're interested in deep learning, we have various model training scripts to get you up and running, and we also have lots of pre-trained models there, which I'll speak a bit more about next week. I know today's not meant to be deep learning, it's just to make you aware of them. But this is a fantastic resource. Pretty much everything there is free, unless it's a third-party piece of software which would ordinarily have a license involved with it, but which case it's just the same third-party license you would need to get anyway. But you know, all the deep learning frameworks are completely free there as well. And again, just to reiterate, we're constantly updating the software which is available there. So it's worth revisiting every few months or so to get the latest version, because you may see a reasonable performance increase compared to previous version, because we're always working to improve them. Okay, I want to say something about unified memory, and this is a very powerful programming tool provided by the NVIDIA runtime drivers. And what it allows you to do is to allocate memory in such a way that both the CPU and the GPU can straightforwardly access it. What happens behind the scenes is, so if you declare this piece of memory, we call it managed memory. When you allocate this memory as malloc managed, then if it's being used on the CPU, the runtime makes sure it's available on the CPU. If you then try and access that memory on the GPU, then the runtime will move it over to the GPU. And it's pretty much as simple as that. That's what happens in the background. And that means as a programmer, it's much more easy to get running with programming for the GPUs, because you're not worried about this data movement. If you just allocate everything as malloc managed, then the drivers can handle this. Of course, the impact of that is that some things may be a little bit slower. You know, as the programmers, we can understand where data needs to be at a particular time, so we could perhaps preempt that data movement. And of course, there are APIs for moving data around more explicitly to allow you to do things like that. But generally speaking, if you're starting to program on the GPU, use unified memory in the first instance. Then, of course, later on, you can go through the profile analysis optimize cycle to check if it's worth your while to actually start explicitly moving data around. In many cases, you find the unified memory model actually does enough for you as well. You don't need to worry too much about that. The VOLTA multi-process service. So this is a great way of making sure you get efficient use out of your GPUs when you're doing things like MPI applications. So it may be the case that you have a certain number of CPU cores running, and you want to attach a GPU to them, and it may be the case that the number of CPU cores you attach is actually out of balance with the amount of work which can be done on the GPU. And this is where MPS comes in. It's called multi-process service, and it helps you balance those workloads between the CPU and GPU tasks. So you can actually assign multiple MPI processes to a single GPU, and they work in a sort of time sliced way on the GPU, but this allows you to make sure that you get the maximum use out of the GPU, because it may be the case, the GPUs are quite powerful, and it can be sometimes hard to make sure you make the most efficient use of all of the GPU. And this allows you to take advantage of the inter-MPI rank parallelism and increase the overall GPU utilization. Okay, when we think about how the GPU works, we have to get data onto the GPU to perform its calculations. So as we mentioned earlier, for a single GPU, that's usually via the PCIe Express bus, which is PCIe Gen 3 for V100 and Gen 4 for the latest cards. However, the PCIe is relatively slow. It's the orders of tens of gigabytes per second compared to the bandwidth on board the GPU itself. So this can be a bottleneck, especially if we're making use of multiple GPUs at the same time. So there are a few ways to mitigate this programmatically. For example, we can overlap data transfer with compute, or we can try and move even more of the calculations onto the GPU. So there may be parts of your code which you currently run on the CPU. You don't think there'll be any particular performance benefit to moving them onto the GPU. But if you do move them onto GPU, you actually may be removing the amount of data movement which takes place. So while the actual pieces of code don't run any faster, the data movement is reduced. So again, we can see a further speed up thanks to removing that data movement. On the hardware side, we have things like NVLink. So I mentioned that earlier. This allows the GPUs to access other GPUs' memory within the same node directly without having to go via the PCIe bus. And it supports much higher bandwidths. On VOLTA, it's up to 300 gigabytes per second between the GPUs. NVSwitch is another technology which we see on some of the boards with 8 GPUs on them. So if you ever come across some of those, so the NVLink feeds are actually directly into the NVSwitch, and that allows all the all-to-all connectivity between the GPUs to be the bandwidth to be greatly increased. In terms of software support for communicating between the GPUs, both within the node and across the node, we have our GPU Direct technology. So this allows you to access GPU memory without going via CPU memory. It takes an extra step out of things, so it can help improve latency and throughput. So this started out with GPU Direct peer-to-peer for GPUs within a node, then GPU Direct RDMA, and this allows GPUs to access each other's memory across nodes. And now in the last year or so, we've just introduced GPU Direct Storage. And this allows the GPUs to get data directly from storage without going via the CPU. So that not only speeds things up in terms of getting data onto the GPU, but also releases the CPU from having to take part in these tasks as well. So it's kind of a win-win in that sense. I'll also just touch on now, we have a new thing called the data processing unit, or DPU, coming out. The idea behind these is to provide a sort of system on a chip architecture with the network cards, ARM cores, and ultimately, hopefully, GPU cores on there as well. And the idea behind those is to manage the data center infrastructure and networking, storage, and security services. And again, the idea behind this is to relieve the CPU of some of this burden. The CPU can especially if you got security things running in the background, a fair amount of cores on the CPU can be consumed by that. The idea behind the DPU is that can handle that as well. And of course, all these different approaches are aimed at ensuring that any bottlenecks at both the node and system level are minimized. Okay, it's all about trying to make things go as quickly as possible. Okay, I'll touch on NVSHMEM. I realize time's getting short, and I'd like to leave a bit of time for questions at the end. So this is a way of writing code for multi-node code for parallel operations across multiple nodes between the GPUs. OpenSHMEM, which is what NVSHMEM is implementation of, is a partition global address space approach to programming. So this has some advantages over MPI when it comes to one-sided communications. And in a sense, it provides a sort of the ease of use of a shared memory programming model, but with the performance of a distributed programming model like MPI. So again, this is a GPU version of OpenSHMEM, which can support that. Tools. Just touch on some of the tools out there. So I mentioned earlier the idea of like profile your code, analyze your code, then optimize your code. Okay, it means that any changes you make to code, you understand what impact it's having. Also, it means you only make changes to the code where it really needs it. And to help you with that, we have the Nsight systems, Nsight compute tools. Nsight systems helps you look at a GPU application in the broader sense of how it's interacting with the CPU, how it's working across a system-wide thing in terms of multiple GPUs across multiple nodes. Once you've done that, there may be a particular kernel, the bit of code that we run specifically on the GPU that we want to look at and optimize, investigate in more detail, and that's when you go down to Nsight Compute, and that's for looking at a specific kernel and making sure we can get the best performance possible out of the GPU. That the Nsight Compute supports roofline analysis, so that you can look at how much of the bandwidth available on the GPU is the kernel making use of, how much of the compute available is the kernel making use of, and you can use that to steer your profiling and your optimization in order to try get a really good idea, understand, are you maxing out the GPU or is there still scope for further improvements? So they're fantastic tools to use for that. And we have IDE plugins as well available for Eclipse and Visual Studio. As an admin person or someone just interested in how your resources are being used, we have the Data Center GPU Manager, DCGM. And again, this helps you monitor the GPUs at a variety of levels. You can look at energy usage, you can look at are the tensor cores being used. So that's a very useful tool. I mentioned the NVIDIA compilers available in a suite called the NVIDIA HPC SDK. This is entirely free. So this comes with all the compilers which support both OpenACC and OpenMP, CUDA, of course, Fortran and C++ and C compilers. It has many of the math libraries already there. It has the communication libraries such as the OpenMPI, NVFORTRAN, which I touched on as well. It comes along with the profilers as well. Sorry, I'm kind of rushing through this bit because I just want to get to the last bit. But as I said earlier, we'll share all these slides at the end, and there are various links on the slides to give you a bit more information. Now, I just want to touch a little bit on HPC and AI. And one of the main challenges for some of the state-of-the-art problems being investigated now and over the next few years is the sheer volume of data which will be produced. And to process and analyze this data in a realistic timescale will require the use of AI. And we've got the Square Kilometre Array radio telescope mentioned here, CERN, fusion experiments. All these are producing huge amounts of data, too much data to actually realistically, practically store. So we need to do analysis or make decisions on that data as it comes in. And pretty much the only way you can do that is to take an AI approach. So this is one of the drivers for combining AI with scientific experiments. And in terms of HPC challenges as well, we showed the graph earlier, things are slowing down, or things aren't speeding up as much as we'd like. It's a very linear relationship between performance and time here. And what happens when we want to look at problems where, where this line's going up, it's just not going to reach the performance we need, and until decades from now. Well, then we perhaps need to think of a different approach, a different algorithmic approach. And one of the approaches we're seeing, which is seeing a lot of really good results, is using AI. And I'll look at a few examples of where you do that. But you can see the green dots here on the upper right. These are just a CFD, computational fluid dynamics. There's molecular dynamics example there, and the LIGO experiment looking at gravitational waves, all of which are seeing orders of magnitude speed up by actually changing their approach to how they're calculating things and taking an AI-driven approach. So this is why there's a lot of interest in HPC and AI. And I'll just touch on a few of the different ways that people are actually introducing AI into their HPC pipelines. So so on the left, we've got modeling and simulation, and this is sort of the conventional HPC. And what we see here, people are embedding AI methods into the ab initio simulations. So they're taking the simulations that you're currently running, they look at it for places where they think the machine learning methods could be beneficial, and they replace whatever current method they're using with that simulation, within that simulation algorithm, with an AI or machine learning enhanced algorithm. And then seeing what the effect that has. And what they tend to see is that either the overall simulation is either faster or more accurate, or in some cases, both. Then in the reduced order model replacement, what we're seeing there, we've seen a lot of traction here. So in your typical workflow, you don't run the full-scale ab initio simulations all the time. You're quite often running reduced order models in conjunction with the full ab initio models. And the reason we use these reduced order models is that they're faster. They may not be quite so accurate as the ab initio models, but they are relatively computationally inexpensive. So you can use those in combination with the ab initio. So what we're seeing now is that people want to actually look at replacing the reduced order models with an AI model. So you take the ab initio data sets, you use it, or experimental data, or indeed data which has been produced by the reduced order model, and we use that to create a training set, which we then use to train the AI, to train a neural network. And what we're seeing in many cases that we're seeing the neural networks can be between 4 to 6 orders of magnitude faster than the reduced order simulation. But quite often more accurate than the reduced order simulation because they've used some of the ab initio data to be trained with. And so you're getting something which is more accurate but runs much more quickly. So that's again one of the reasons that people are so interested in taking these approaches. It really opens up new avenues of research. On the right we have the experimental data processing side of things. So we can put improvements in the pipeline here by taking AI methods. So if you take things which are well understood from AI, such as image recognition or signal detection, we can apply those in these scientific experiments and see a great performance increase in terms of increased accuracy. So we've got an example here from Fermilab, where they've seen a 49% increase in performance of the accurate detection, which effectively means that their large collector here is effectively 49% larger without actually having to build it because it's more accurate. And then what I think is real interest is the AIs can make decisions so quickly and so accurately that we can actually start looking at real-time control. So for example, in this idea of fusion experiments, we want to make sure that the experiment remains under control, and with this idea of applying AI, we can actually have real-time control over it and make sure the experiments last longer. So I think that's a really interesting approach. Okay, we are nearly at time, so I won't go through these slides, but they are included in the deck, so you can have a look. It's basically resources for you to go and have a look at. And just to give a heads up, we have got a GTC conference happening in November, which you just need to register for, but it's free once you're in. And there's lots of information, lots of interesting talks happening there. And I will stop there. Oh, actually, no, sorry, one more slide. Just to stress again, keep everything up to date. Looking here, this is a graph showing the performance of a basket of codes during the lifetime of the V100 between 2017 and 2019. And it went from 2x performance over the P100 up to 4x. That's purely through software improvements. So if you didn't keep your applications and libraries and frameworks up to date, you'd still be running at 2x rather than 4x. And of course, those improvements are still going on now as well. So just keep everything up to date. Right, I will stop there. Any questions? I've stunned everyone into silence. All right, let's just look at
I actually have a question concerning the Dockerization of code.
Mm-hmm.
So in my experience, we have to reboot after we upgrade the libraries, because the libraries of the code that was, it needs to match, otherwise we get crashes. How does that work with a Dockerized application?
Well, it's everything's sort of self-contained within the container itself. So you should just be able to, download a new version of the container, and that should just run. You shouldn't affect the hardware at all. No need to reboot. Unless you got, maybe something like if you got a more recent version of Docker or Singularity, then there may be some need to reboot there. I've not ever tried it, but in terms of, you just get a new version of the container and you can just run that straight away. You don't have to reboot the hardware at all.
Matching the library that's installed, because in my experience with Docker, like if you use GPUs, you just like it maps somehow. It does the magic to map through the libraries that are installed on the host.
Yeah, it's all contained within the container. I mean, And also the way the runtime drivers are set up, that they have backwards compatibility and things like that. So if there's a mismatch of versions, you're usually okay.
Oh, okay, I'll have to play around with it then.
Yeah, but by all means, I'll put my, if you're having an issue with something you want some help with, I'm more than happy to give you a hand. I'll put my email in the chat. The same goes for anyone else who's got any questions or any follow-ups and things. I know I've covered a ton of material today and had to rush through it at the end. And I've just touched very lightly on a few things. If there's anything anyone wants to have some more in-depth knowledge about, I'll be more than happy to try and help with that. So,
thank you.
You're welcome. Yeah, the slides are going to be available. I'll share the slides. And as I said, anything which is sort of green in the slides is a live link. So you'll be able to click on that and find out more information.
Arno, please.
Yeah. Hey, Paul. I just had a question. I had a question about the MPS, the multi-process service. So I know on some Cray machines, for example, there used to be, or is maybe still, some environment variable Cray CUDA MPS which you need to enable to enable that. I've seen a reference to some NVIDIA, some CUDA runtime settings, or maybe even boot up settings to launch a control daemon to make that work. Do you know if this is current, or if it's currently
yes.
what needs to be configured by sysadmin?
Yeah, you do need to set up the MPS service for it to be used, because there are some systems that people don't want it to run. So it's something you actively need to enable. I think I mentioned GROMACS there. There's actually a blog there which mentions MPS coming up for GROMACS, which isn't on there. Sorry, I haven't got a link to that yet because it's not published yet, but there's a great example of using MPS with GROMACS, and actually goes through the steps you need to do to get that working. And you actually see quite a significant improvement in the throughput of GROMACS by enabling MPS. But there are some steps you need to take to get it up and running. But that's all well documented.
Cheers, thanks.
Okay, so that's the hour. Just say thank you, and hopefully see some of you next week if you're interested in doing deep learning in AI and what's possible. Hopefully you found it useful, so thank you for that.
Yeah, thanks, Paula. Thanks everyone for joining. See you hopefully next session next week. Thanks.
Thanks a lot.